Hello, Denise. Are you there?
Hi, Mr. King. Can you hear me?
Yep.
Okay.
How are you doing?
Good. Thank you.
Good. How does the my voice sound? The same?
Actually, yeah, somewhat.
Yeah. I don't know what's going on, but it's not too bad.
No.
Okay. So, okay, well, let's see. What can I do for you? Let me go to your class. Do you see the web assign page?
Yes.
And um, so for this class, we talked about the integral series test. Oh, yeah. And then I told you that if you wanted to wait on, let's see here, it was 15 and 11 and 10, 11 and 15 till tomorrow.
Mm-hmm.
And then, so that's where we are. And so now this is the office hours or 30 minutes. So
Mm-hmm.
what can I do for you? So I guess I
Uh,
can help you with any specific questions you might have.
yeah. For number one, I don't understand how it's supposedly getting closer to infinity when I take the limit, it goes to zero. So I'm just confused on whether to do it observationally or to just go straight for the limit. Like, what's more certain? What should I do?
So, well, I would use, to answer your question, I would go straight to the computation of the limit, but
Okay.
your answers should coincide. And
Yeah, I guess that's what's also confusing me. Like, I know if I get zero for the limit, then my observation should get closer to zero. And maybe I'm just not observing it right. I just need some more clearance on
oh,
that because
I
it's confusing.
saw your picture and you emailed me, and I sent back a response, and I
Yeah.
wrote that those terms as they go out, the 2 stays the same in the numerator, huh?
Mm-hmm.
And the denominator keeps getting bigger every term by 3 more. So
Right.
it's like 2 over 4, and then 2 over 7, and 2 over 10, like that, huh?
Mm-hmm.
So what happens when you have the number in the numerator is not changing, but even if it was, the denominator is getting bigger faster. So what happens when you have, in this case, 2 all the time, and then divided by a larger and larger number, then those numbers are going to get, what's that value of 2 divided by a larger and larger number?
2 divided by a larger mark, that goes to zero.
Yeah. And that's what you said when you took the limit.
Yeah, when I took the limit, I saw that, but I guess I'm not observing it right because I don't
Yeah,
know what I'm using my calculator, but I guess I don't know what I'm doing wrong.
it's
I'm
okay.
just gonna go straight for the limit because,
So can you see my Desmos calculator now?
yeah.
So um, so 2 over 4, and then 2 over 7, and then 2 over 10, and you can see 2 divided by 13. These numbers are getting, the value of these fractions, which are the individual terms of the sequence, they are um, getting smaller, aren't they?
Oh, yeah. Yeah. Okay.
So I don't know if you were, I don't know what you were doing, but
I was adding all of those up. I thought we were supposed to add them up.
oh, that's the second topic of interest is
Oh,
what
okay.
happens when we start to add these terms up, right?
Yeah. Okay. So the first thing we do is see what's going on with the numbers, not necessarily add them up.
Right. Uh-huh.
Okay. Yeah. Okay. That clears everything up. Okay.
Because if these numbers individually don't get smaller and smaller, closer and closer to converging to zero, then then the second question is already answered for us, that if these terms right here individually are not getting smaller, closer and closer to zero, then when we start to, if they're not, then there's no way if you add them up forever, they're going to be able to converge to any finite single number. So
Okay.
now if these do individually get smaller and smaller, closer and closer to zero, in other words, the limit of the individual terms of the sequence converges to zero, then there we know there's a chance that, at least a chance that when we add up these terms forever, that it could converge, that sum, huh?
Mm-hmm.
Does that kind of sound familiar now?
Yeah.
Okay, so then on number one, I can, do you want me to continue with this problem, or do you think
Yeah.
you can go from there, or do you want me to just to work it out?
Yeah, can we work it out? That's the only one that kind of...
Sure. So let me
Please.
switch here. So it's 2 over 3n plus 1. Okay. Okay. And you can see my notebook now?
Yes.
So this is so that's supposed to be anyway. This is number 1, and we were given the formula 2 over 3n plus 1 from 1 to infinity. So again, I just feel it helps if we write the first few terms down.
Mm-hmm.
That goes on forever, of course. And if we put so all of these are fractions with a 2 in the numerator. And I saw this is what you had on your paper that you sent me. And the first one is when you put a 1 in, 3 times 1, 3 plus 1 is 4. And then it has this, the denominator is increasing by 3 every time. So yeah. Can you hear me okay?
Yes.
Okay. So the first thing we want to know is individually what's happening with the terms of the sequence, even though in the questions they don't even ask us that question. But we're supposed to learn that that's the most logical thing to do first, is to find out if the individual terms of the sequence here don't converge to 0, then we're done with the question that they want us to answer. Because then the sum of all the terms would have no chance at all to converge, and we would just be done and say diverges, yeah?
Yeah.
That's if these, so if these terms individually do not converge to 0, then we're done already in terms of what they're actually asking is to add all these up. Then we'll say it diverges and we're done. By the nth term test for divergence, yeah?
Yeah.
So when we do, so the first step, at least, well, that's my opinion, but first step is to take the look at the limiting value of the terms of the sequence individually, and we can do that like we just did up here, and we did it in the calculator, and observationally it did seem like they were going to 0, and then if computationally you get 2 divided by, put infinity in, and now we're about to perform limit question by substitution first. if we get a determinate value, then we're done already. And if we, which is converging is a single finite number, diverging is infinity only, negative infinity only, or some kind of alternating, oscillating situation where it would diverge. So if we get an indeterminate, when we substitute our limit question, it could be an unfriendly indeterminate or a friendly indeterminate, and we would proceed as we've been practicing. So
Cool.
what happens on this first attempt to take the limit by just substituting? Do we get an unfriendly indeterminate, a friendly indeterminate, or a determinant? Yeah. So
We
what
get
is, I'm sorry?
we get 0 as a determinant.
Yeah. So good. So this is a determinate value. When we took the limit, we were able to determine that the limit is 0. That is a single finite number. It converges. And it converges to 0. And so then that's supposed to tell us something from our strategy. And so that means, and remember, if it converges to another number except 0, if it converges to a single finite number other than 0, well, then we would be done as well. Then there would be no chance for these, because if they just pretend if they converge to 3, and that would mean as you go out forever, these individual terms would get closer and closer to 3. And so if you start to add all these up, and knowing already that the individual terms are getting closer and closer to 3, well then if you keep adding them up, there's no way that the sum could converge towards a single finite number. Because, okay, I'm adding up the terms, and now I'm close to 20, and I add the next term. Well, the next term is it's almost 3. So if you add something that's almost 3, well, you're going to pass 20, and then you're going to pass the next time, you're going to be around 23 and around 26. And so there's no way that the sum could converge. Does that make sense?
Okay. Yes.
So the only way that these terms could, when we add them up, have any chance at all of converging to a single finite number is if the individual terms themselves are converging to 0.
Okay.
Is that okay?
Yes.
So now that means we need to further our exploration here and analyze with a series test what the sum of these terms, if they do converge to a single finite number or they don't. Yeah?
Okay.
Now when we talk about the sum and we talk about converging, they're not going to converge. When they say a single finite number, that doesn't mean it has to be 0, and can't be 0. If these are not alternating, so these are positive numbers. So there's no way you add them up, you're ever going to get to 0. It'll be some. If it does converge to if the sum of all these terms forever does converge to a single finite number, it will have to be something other than 0. It'll be something bigger, right?
Okay.
Okay. So anyway, now we need to use one of the 9 series tests that are coming, and we only know 2 of them. Yeah, and it's geometric and the integral series test. So this, even though that's a 2 on top, but there's no way if we tried and we looked for a common ratio, if you took 2 divided by 10 and divided it, I just picked one of these, divided by the one right in front of it, then you changed it from this division to multiplication, well, that would be 14 over 20, but you could just reduce it to 7 over 10. So that's one ratio of 2 consecutive terms. If you picked another 2, if we get 7 over 10, well, then it's geometric. Yeah?
Okay.
So if we pick two more and change this from division to multiplication, the twos divide out, and now we're left with 4/7. And that's not, they're not equal, are they? So that means, do we have from one term to the next, into the next, into the next, do we have a common ratio here or not?
No. No.
So, I don't know what I was gonna write here. I can't read my writing.
Not geometric? I don't know.
Yeah. So it's not geometric. Oh, I was gonna say not a common ratio, but I don't know what I started to write. So I had a 3.5-hour class before this one, so I'm a little.
Oh my gosh.
Yeah. Although I had a 20-minute break, so that helped. So we don't have a common ratio, so it's not geometric.
Okay.
So we can't use the geometric series test because it's not a geometric sequence, huh?
No.
So then what's our only test that we have learned so far?
The integral series test.
Good. And what in order to use the integral series test, we would have to be able to change this to a function and be able to integrate it. So before we even check the conditions to see if we can use the integral test, I hope it makes sense to just say, check in our mind, could we integrate this if we are able to use the integral series test? Then I guess they do write infinity there. So so this multiply 2 could go out in front. You'd have a 1/3x plus 1. And so whenever you have a 1 over in the integrand, if it's 1 over, then our mind should, hopefully, with practice that we've been having, is to think of it, can I let it be a 1 over a u or a 1 over a w type? Yeah? So if we did do that, and we know that the integral of 1 over u or 1 over w from our antiderivative formula sheet is a natural log of absolute value of.
Right.
So if we do rename this on the bottom a single letter, then we'll have integral of 1 over u or whatever letter. And then what's the derivative of that renaming statement going to be?
Dx.
And what's the derivative of the 3x plus 1?
3.
So won't it be okay to be off by a multiplied 3? And then we can use the plot method or the traditional method to compensate it and then be able to integrate it, huh?
So I couldn't take out the 2/3?
You cannot take, if there was no plus 1, then this is 3 times x, and then it would just be 1 over 3 times x. And if that was the case, then it wouldn't matter if we could write this as 2 over 3 times 1 over x. Because numerator times numerator is still 2, bottom times bottom is 3x, but we have a plus 1 here, don't we? So maybe this helps, I don't know. If we have 2 times 1 over 4 plus 7 in this room? Oh, I'll wait about 20 more minutes. Okay, sorry. So if we had this, Denise, well, this is equal to 2 times 1 over 11. 4 plus 7 is 11. Okay. If we were, can we also do this then? 2 times 1 over 4, and then, I don't know, trying to think how you were thinking of it here. You said pull out this 3. So that's not the same thing as now. Now I guess I could write 1/7. This 4 cannot come out separately as this.
Okay.
Because if you multiply 2 times 1/4 times 1/7, you will not get 2/11. You'll get 2 times 1 is 2, 4 times 7 is 28. That's not the same thing as 2/11. Not sure if I'm finding the right words to convince you why.
Yeah.
Only if you could I guess you could do it this way. You could factor out the 3 by doing this. 3 times x plus 1/3. Because 3 times x is 3x. 3 times 1/3 does get back to 1. And now that we have factored out the 3, you could write it as 2/3 times 1/x plus 1/3. That would be,
so that's when it would be okay.
That is legal to do that. We could do that right now if we wanted to. There's really no advantage of doing that. Really, if there's any advantage, it's very negligible in terms of the use substitution step.
Okay.
The only advantage would be is now but that's thinking too far in my opinion, because what's now the derivative? If you rename this W, what's going to be the derivative of that statement?
1.
1. And now you don't have the extra multiplied 3 like you would have if we left it like this. But that's the only difference. Okay?
Okay.
But I don't think it's really worth that effort or that opening up the new door to another set of possibilities. But it'll be up to each individual, I guess.
Okay.
So, is that okay?
Yes.
So let's not do that. Okay?
Okay.
So all this is nothing now. Okay, so now, but I hope you agree, we will be able to integrate this. And also we could have integrated it if we would have factored the 3 out, but then it would have been this plus 1/3 instead. So then since we know that we can integrate this if we're allowed, meaning if the 3 conditions are satisfied to use the integral series test, well, then we know when we go about to integrate this improper integral, we will be able to anti-differentiate it. Yeah?
Okay, yeah.
So then it makes sense to check the 3 conditions. The three conditions in order for us to use this integral series test. And we were saying yesterday, we can determine this informally by just looking at the graph, which will be this 2/3x plus 1. And then we'll make a little sketch of it, and then we will check those 3 conditions. And can you see the WebAssign page?
Yes.
Okay. And now the Desmos page, and we'll look at this graph. And I feel like that's the right graph. And but we're not concerned with this part over here, because we're only interested starting at 1, n equals 1, or when we change to a function, x equals 1. Yeah? And we keep getting this similar looking picture, don't we?
Yeah.
Because why? What are the 3 conditions? They have one of them in no particular order.
It has to be positive,
So is all this graph here starting right here, starting at n equals, or looking at the function x equals 1, so we don't care about this side over here. We only care about starting right here. And if even if the initial pieces of it were underneath, that would be okay still, as long as eventually everything is positive. But anyway, this is all positive, isn't it?
Yes.
Because it's all this graph, all these points on the function f of x are above the x-axis, even though here it gets super close, but it's still above.
Okay.
So there's one condition met. Okay. What's another one?
It has to be continuous.
Good. And how would you tell someone, convince someone that this is continuous?
If there are no vertical asymptotes.
Good. Or any holes in the graph, or any pieces broken up and separated. This is a separate piece over here.
But that's not what we're worried about, right?
Correct.
We're worried about the right side. Okay.
So actually, there's a discontinuity at the vertical asymptote over here. And this bottom part equals 0, but that's at x equals -1/3, and so we don't care about that. Okay.
All right.
So it is continuous for x greater or equal to 1. And what else? What's the missing one? We're still.
It has to be decreasing.
And again, if it's not decreasing initially, if it was going up a little bit and then it started to decrease, that's okay. Yeah.
Oh.
As long as once you get to a certain place, then it just stays decreasing from then on. Okay. And like that first problem we did yesterday, it I think if I remember, it went up a little bit and then it started to decrease. Yeah.
Yeah, it did.
Okay. So, but this is decreasing forever, isn't it? Starting at 1, or you can say right for greater than 1, or however you want to say it, but this is decreasing forever, isn't it?
Yes.
So then, are all 3 conditions met then? Are satisfied?
Yes. Yeah.
So then on our paper, we write those down. And so I'll switch to my notebook, and I want to come back to Desmos for a moment yet. But so f of x and it doesn't really matter which ones the order. So I think I don't know what you said first. I think you said positive, but it doesn't matter.
Positive, continuous.
Really, you could write it in one sentence if you wanted to. I just write it separately to keep three thoughts separate. So once you are comfortable with it, a person could write f, and also if all 3 are the same thing, like these were for x greater or equal to 1 on all of them. So then if you wanted to summarize this, instead of writing it separately 3 times, you could say f of x is positive, is continuous, and decreasing for all x greater equal to 1. There could be an argument about at the decreasing part at x equals 1. I'd have to go back and look at the graph. But anyway, certainly but let's not get into endpoints and stuff, so that's okay. So, so continuous, and decreasing. Okay. Oh, and then our sketch was something like. Oh, yeah. And it is decreasing for x greater equal to 1 because there is a graph right over here as well. And it wasn't like open right here or something. Okay, so therefore the conditions are met, and thus we can use the integral series test. Or we can proceed, or however we want to write it. Since we can proceed, then now we want to analyze what is the understanding of the integral series test is if those three conditions have been satisfied, then to answer the question of what, because these are these little mappings at 1, at 2, at 3. So right here, this right here is your 2 over 3 times 3 plus 1, which is the 2 over 10. And this one is when n equals 2, the 2 over 3 times 2 plus 1, like that, and forever. So that would be, that's one sad looking 2 here. Anyway, 3 times 2 is 6 plus 1 is 7. So that's the 2 over the 7. And the 2 over the 10. And this one right here is 2 over 4. And so now our question that we're being asked is, what happens when you add this term plus this term, which is 2 7s, plus this term, which is 2 10ths, plus this term, which was 2 over 13, and so forth forever, huh? And the first thought is, well, these individual terms have to be converging to 0 as individual terms of the sequence, and that was the first step we did. That was that limit that we did when we first started this, and the one that you had a difference in your mind that initially, that observationally you thought it was different than 0, but then now we're convinced that it's 0. So then that means there's a chance that when we add up these individual terms forever, it could converge to a single finite sum, or some value or numerical value, or it may diverge. So what do we need? We need a series test, and we know we can't use the geometric. We know we can use the integral series test because the 3 conditions were satisfied. And now to answer the question of, do these individual terms, which is this height, this function value forever, does it converge to a single finite sum number or value? We, instead of adding these up, we are going to use the integral series test, which is to say, well, what about the area underneath this function instead of just adding up these heights, which are these numbers here of the terms of the sequence? Instead, we're going to analyze the area of this underneath this curve that goes out forever, which makes this an improper integral. Now, does this area from 1 to infinity converge towards a single finite area value, or not? And if it does, if this area from 1 to infinity does converge to and as soon as you say converge, we're being redundant if we say to a single finite number, because that's what converges means. I'm just trying to emphasize. And then, so then if this area converges to a single finite number, then these individual terms will also converge to a single finite number, but it'll be a different number, okay? Than the area. Does that make sense?
Yeah.
And if this area diverges, which means it just keeps getting bigger and bigger forever, which means it never gets closer to one single number, like whatever, 17, it passes 17, and then you keep adding number, or I'm talking about area, but if the area does not converge, that means it diverges, and then so will the individual terms of the sequence will also diverge to infinity.
Okay.
Okay?
Yes.
And now we're gonna check. What about the area underneath this curve? So in terms of we're gonna actually write the integral down on our paper, but just for curiosity and exploring purposes, we could ask Desmos to integrate, and we want to start at what x value? The starting
One.
end value. What did you say?
1.
1. And let's just say we go out to 10. Excuse me. So this is the area from 1 to 10. So this pink area here all the way out to 10. And because we're stopping at 10, and there's no vertical asymptote here, this is what we get, 1.365. But that is not what we would get if we added 2 4s plus 2 7s plus 2 10s plus 2 13s plus this, because well, if you start to add up just the first few, 2 4s plus 2 7s, we're already at 0.78, and plus, well, I should be careful what I say here, plus 2 10s, oops, plus 2 13s. So 2 16s. I don't know if I want to go all the way out to 2 over whatever 10 is. 10 would be 30. 3 times 10 is 30 to 31. So, I mean, we could keep going here. But 2 over 19, and we already passed this number above it. Oops. 2 over 22. And see, we're already past this, right?
Yeah.
Oh, but I just wanted to give you an example that the area underneath the curve is one question of computing area under the curve, and adding the terms of the sequence, which are just these range values, these heights, yeah, of the individual terms of the sequence, is a different sum. It's a different number. But if the area converges, then so will the sum of the individual terms. If the area underneath does not converge, which means it goes larger and larger to infinity, well then when you add up these individual terms, they also will diverge to infinity. But if the area converges towards whatever, let's say we end up getting an, by the way, we're only at 1.365. If we go further, say we go out to 20, where now we went from 1.36 to 1.81. Now the question is, we've only done 2 integrals. Do you think this is going to keep getting bigger and bigger forever, diverging to infinity, or Is it going to converge, getting closer to 2 or something, or 3? And right now it's kind of, huh?
I think it's gonna diverge.
You think it's going to diverge? Okay. So if we go out to 100, we made it to 2.88, huh? And you could just keep going. And eventually the computer is going to have trouble, and it might. So there's 4. So you're probably right that it's going to diverge to infinity, huh?
Yeah.
And that will mean then by the integral series test that if the improper integral, which is the area, diverges to infinity, then when you add up these individual terms, they will also diverge to infinity.
Right.
Is all that making sense?
Yes.
Okay. So now we go to our paper, and we're gonna, and by the way, we got, well, you already said it's gonna, you think it's gonna go to infinity, so okay.
Yeah.
So now we're gonna work on the actual integral, pull out the 2, 1 over 3x plus 1. And this is from x equals 1 to infinity. That's what makes it improper, which means it could converge or diverge. And to do this, well, first, we're going to change this from x equals 1 to infinity to 1 to b, where what? The limit
as b reaches infinity.
Of the same integrand expression. And so this is what we are, that's our mission. And you already suspect that it's going to equal infinity, which means diverge. Okay. And so now we just have to be able to integrate this. And we talked about that earlier. So if we let a single letter, whether it's a W or a U, just don't pick X here. Then when we differentiate this renaming statement, we are renaming the 3x plus 1 into a single letter so that we can use our antiderivative formula sheet. And then you take this renaming statement and you always differentiate it with respect to the original variable of integration, which is whatever's here. So we get what? dw over
dx.
And then we're going to move the dx onto the other side by multiplication. And what's the derivative of 3x plus 1 with respect to x?
3.
And now we rewrite our integral. And we have this limit still, that's waiting for us, as well as the multiplication of 2. So until we've anti-differentiated it and evaluated the upper limit and the lower limit, then we take the limit as the final step in determining the value of this improper integral. Technically, we're not supposed to write 1 here and a b right here because now it's with respect to a new letter. And so here we have 1 over w. And now we check. 1 over w takes care of the 1 over 3x plus 1. The dw takes care of the dx. And then there's an extra multiplied 3 in this dw statement, or underneath the dw statement, however you want to look at it. And therefore, that wasn't there before. There was not a multiplied 3 up on top before. So now we have to compensate by multiplying by 1 over 3. Or we could do it traditionally, and that would be solve for dx, and we would get dw over 3. And then when you rewrote your integral, you would have 1 over w, and then instead of the dx, you would directly substitute what dx equals, and then you would have dw over 3, and then this 1/3, this division of 3, which is like 1 over 3, you could put out in front as well. So either way, with traditional method on the renaming part, or just sort of plopping it and then adjusting it, it works out to be the same integral, huh?
Yeah.
Are we okay with that part?
Yeah, we're good.
So continuing with our attempt to anti-differentiate, we have the limit still, the times 2/3 still, and now we are able to integrate 1 over a single letter with respect to that same single letter from our formula sheet, or just remembering in our mind. And either way, what did we say that turned out to be?
The ln of u.
And then good, and let's not forget the absolute value. Okay, and then go back. This was a newly created variable so that we could integrate it with the formula sheet. And so now we have to go back to the original variable, which is the x. So we have ln absolute value of 3x plus 1 was our expression for the single letter, and then from x equals 1 to x equals b. Any questions here?
No.
So what do we do now? What do we do?
Now you're gonna do the fundamental theorem of calculus.
And
And take the limit.
That'll be the last step, huh? And then we input the upper limit of integration, x equals b, the lower limit of integration, x equals 1. And so what's going to happen, instead of the ln of absolute value of 3x plus 1, we're going to have everything there except for the x value on both of these. Oh, and then absolute value, sorry. Same thing here. ln absolute value of 3 times, I should wait on these grouping symbols. I'm sorry. So So what are we going to put right here, Denise? Instead of x, we're going to put what on the front?
We're gonna put b.
And here we're going to put in
1.
Which is the upper limit of integration first and the lower limit of integration secondly. Yeah? Now, clean this up. And then the 2/3 can wait for us to take the limit. So So this is natural log absolute value of 3 plus 1 minus 3 times 1 is 3 plus 1 is 4 minus the natural log of absolute value of 4. Okay, so we integrated it. We evaluated it using the first fundamental theorem of calculus, like you said earlier. And that means, because this was an improper integral, there's going to be a b here somewhere. And now we're going to take the limit as b approaches infinity, and we're going to find out in a moment if this improper integral converges to a single finite area or numerical value, or it does not converge. And in this case, it would have to then, if it diverges, it would have to be to positive infinity, because the area was above the x-axis. So anyway, so is this term right here going to be affected by when we take the limit as b approaches infinity?
No, just the first term.
Yeah, because there's no b here for us to take the limit as b approaches infinity. So this stays the same. So the 2/3 is still waiting. By the way, the absolute value of 4 is still 4, so you don't. So that's simplified. And now, what happens when we put infinity in right now? We hope we'll get a determining value for this limit value, or if not, we'll get an indeterminate, which could be an unfriendly one or a friendly one, and then we would proceed if that happens. But let's hope we get a determinate value right off the bat and we're done.
Okay.
So what happens, of course, if we put this infinity right here, we just substitute it in and see if we can get a determining value for that limit question. So 3 times infinity, of course, is infinity, plus 1 is infinity. How about then the absolute value of infinity is infinity? And what about the natural log of infinity?
That's infinity.
So that means, presto, I'm about to write a determining value, huh?
Mm-hmm.
And it's infinity. And now complete the rest of this simplification here numerically. Well, infinity minus ln of 4 is some number, but infinity minus any number is still infinity. Times 2/3 is still what?
Infinity.
And so what does that tell us then? Our improper integral, therefore the improper integral diverges. And we're not going to get, with this integral series test, we're never going to get the improper integral diverging to negative infinity, because then the graph would have, the terms would have had to have been negative terms underneath the x-axis, and then we couldn't use the integral series test anyway, yeah?
Okay.
So same with the oscillating, because for it to be, well, I'll just leave it at that. Okay, so.
Okay.
So what does that tell us then, Denise, about if we now, remember, the ultimate goal was to, was analyzing the individual terms, that number plus that number. And by the way, you were right, the improper integral did diverge, and therefore this number plus that y value plus that forever, which is the same as these terms right here, forever, which is the same as way up here, was looking at the individual terms of the sequence. And now we know since the improper integral diverges, then what about the sum of these terms of the sequence? They will also what?
Diverge.
Diverge. Is that okay?
Yeah, perfect.
And that's what this first step was. Yeah, the individual terms do converge to 0, but that only gives a chance for the sum of those terms to converge. They still may not converge.
Yeah, and this one's one of them, right?
That is
this one
correct.
diverged. Okay.
That's correct. Very good. So therefore, or thus, or so, whatever, the series, which is just a fancy way to say the sum of all these terms starting at 1 forever, must also what?
Diverge.
Diverge. And which one? Which type of diverge?
To infinity?
Now, they may not ask, but they may, or they may. By the integral series test.
Oh, okay.
Any questions here?
Nope. That's it.
Okay, so we go back to WebAssign, and we know that this diverges, which means the series, and it's because of all the work we did, and then and at the end it was because the improper integral diverges. So they might want us to type in the word diverges here or put infinity, and I think somewhere along they gave us one where we had to put infinity, and I'm not sure. But this one, what do they want us to put? Infinity?
The infinity.
Oh, you're right. So here they do want us to leave it as infinity. Okay. So put infinity, and now check. If we would type diverges here, they probably wouldn't give us credit. You know? And we are good.
Cool.
Does that make sense to you?
Yes.
Okay.
Clears it up.
Good. I think you just kind of got hung up at the beginning, and then that kind of shook you up a little bit, yeah? That happens to all of us, especially me. Okay, Denise. So I hope that helps you, and I hope you can try or if you didn't get the rest of them done, you can work on them, and then, well, hopefully we will speak again tomorrow. Okay?
Yes. Awesome. Thank you so much.
You're welcome. Anything? Any question or comment about this one?
No, nothing.
Okay.
Everything's clear now. Thank you.
You're welcome. Okay, so we'll talk to you tomorrow then.
Yes. Bye-bye.
Okay, goodbye.